CORLEO moves on 4 robotic legs, each one designed to mimic the way animals like horses navigate rough ground. It can walk, jump, crouch, climb, and stay balanced even on uneven or steep surfaces. Its back legs use swing arms inspired by motorcycles, helping with stability and shock absorption. The feet are split-toe rubber hooves that grip well on slippery or loose terrain like snow, rocks, or mud. Power comes from a small hydrogen engine, not to turn the legs directly, but to generate electricity for the motors in each one. The only thing it emits is water vapor, and it runs almost silently. A hydrogen canister fits into the back of the frame. Riding it feels more like riding an animal than driving a vehicle. You steer by shifting your weight, forward, back, or side to side. The foot stirrups adjust to fit different riders, and real-time sensors help it stay balanced. On the dashboard, you can check hydrogen levels, see how tilted the machine is, follow navigation cues, and even get night visuals projected on the ground ahead. Kawasaki created CORLEO around the idea of movement that breaks free from roads. It's not a car, a bike, or a drone. It's something entirely new, meant for places where wheels just don't work. Think dense forests, rocky hills, mountain trails, riverbeds. It can go where trucks can't, and do so quietly, without tearing up the ground. It's still a concept for now. Hydrogen refueling stations are rare, and the tech behind its autonomy is still evolving. Full production isn't expected until around 2050. Meet Charlie. This robot is designed to move like an animal, and sometimes even stand like a human. In its regular 4-legged stance, it measures about 66 by 43 by 75 centimeters, but it can stretch up to 130 centimeters when upright. It weighs between 18 and 21.7 kilograms and runs on a 44.4 volt, 2.5 ampere-hour LiPo battery. Inside, it's packed with a mix of motors. 8 48-volt RoboDrive units with 2 different gearings, plus 10 Faulhaber motors that give it precision and control over its movements. Its feet aren't just for walking. They each contain 43 pressure sensors to read the ground beneath, plus 6 extra to detect collisions. It also carries a 6-axis force torque sensor, heel distance sensor, magnetic encoders, temperature monitors, and a 3-axis accelerometer to help it understand its posture and surroundings. Connecting its front and back halves is a flexible spine-like joint with 6 degrees of freedom. That spine isn't just for movement. It's part of how Charlie senses physical forces through built-in load sensors. The robot tracks everything happening in its joints, including speed, position, power levels, and heat. It has a central unit to manage the big picture tasks, while smaller processors in each limb handle quick, local decisions. Developed by the DFKI Robotics Innovation Center in Bremen as part of the iStruct and Vipe projects, Charlie was designed to navigate rough terrain, like Martian valleys. It can walk at speeds up to 1 kilometer per hour and handle slopes up to 20 degrees. One of its standout moves is a self-righting routine, where it flips itself from lying down to standing up using its spine, with the help of machine learning. With over 330 sensors built in, Charlie serves as a testing ground for research into balance, movement, and how machines might one day navigate the same kinds of landscapes that challenge animals, and even humans. This flying device packs a surprising amount of engineering into something that weighs just 12.2 grams in the air. Its frame is made from carbon fiber with a tough internal core, while the wings, tail, legs, and head stay flexible to soften crashes and protect the delicate parts inside. The wingspan stretches to 38 centimeters, giving it enough surface area to glide smoothly without losing speed or control. At the heart of its movement is a custom micromotor that puts out 1.6 watts, spinning at up to 53,000 rotations per minute when idle and around 35,000 during flight. The wings beat up to 18 times per second at about a 45-degree angle, pushing enough air to generate 11 grams of thrust, more than enough to let it dart and turn with precision. Wing motion is handled by a patented flapping system and a tiny speed reducer, allowing for steady, efficient movement. Steering happens through wing flexing, which gives it quick, tight turns. The tail can be adjusted to one of 4 positions, giving the user control over how fast or stable the flight feels. Onboard sensors track movement and balance, keeping the flight path smooth and helping prevent stalls. The flight software was developed with input from military research teams in France. Power comes from a small 58 mAh battery that can be swapped in seconds. No tools needed. It charges in about 13 minutes and provides up to 10 minutes of flight. Built-in safeguards help protect the battery from damage. A Bluetooth 5.2 connection extends control up to 150 meters away, and the companion app offers 4 ways to fly: tilt controls, a one-finger mode, a traditional twin-stick layout, and an option for joystick users. It flies at speeds between 5 and 20 kilometers per hour, handles light wind well, and can take off from your hand or a smooth surface. Meet Quadroin, a robot inspired by penguins, designed to take on a wide range of underwater tasks with speed, precision, and smart onboard systems. It measures just over a meter long, with a 304 millimeters diameter and a total weight under 25 kilograms. Its shape, modeled after an Adelie penguin, helps it move through water with minimal resistance. 4 electric thrusters arranged in an X pattern allow it to reach speeds of up to 5 meters per second, while its internal battery supports more than 10 hours of operation at cruising speed. Recharging takes less than 6 hours. The Quadroin can dive as deep as 150 meters and uses an advanced navigation system that blends Doppler velocity log, attitude and heading sensors, and inertial guidance. When it surfaces, it connects to satellites using GPS, Galileo, or BDS to update its location. It can also be paired with long baseline positioning systems and includes acoustic technology to help it detect and avoid objects in its path. For communication, it uses Wi-Fi, ISM band radio, or optional satellite uplinks when on the surface. Underwater, it sends data through a compact acoustic modem with an atomic clock for timekeeping. A pop-up antenna handles surface signals, and LED markers help with recovery. Inside, it runs on an ARM Cortex-A7 processor with 512 megabytes of RAM and 64 gigabytes of storage. Its onboard AI lets it make sense of what it sees and hears in real time. The system can carry up to 3 kilograms of sensors or gear. It's equipped with 2 HD cameras, one looking forward, one downward with adjustable lighting. Depending on the mission, it can use sonar, current profilers, CTD sensors, magnetometers, and other tools to measure ocean conditions. Launched from land or boat, it follows set paths, collects data, and sends back findings during or after the dive. It's used in marine science, seabed exploration, port inspections, and synchronized group missions. Titanoboa robot stretches 50 feet long and weighs more than 2,500 pounds, with its widest point measuring about 2 feet across. It's made up of over 30 connected segments, each built with aluminum alloy frames and strong steel joints. Inside each segment runs a central shaft that holds the wiring and mechanical parts. It moves using both hydraulic and electric systems. Servo motors and pneumatic cylinders in each section work together to mimic muscle movements, letting the robot slither, crawl, and undulate in a way that looks surprisingly lifelike. Power comes from a high-capacity lithium polymer battery, and everything is managed by a central computer. The robot can be guided remotely or programmed in advance. Each segment is packed with sensors, including IMUs, gyroscopes, accelerometers, and position trackers that help it stay balanced and move smoothly. This machine was created by a team known as the Titanoboa project, made up of engineers, artists, and robotics experts working with the Eat Art Foundation in Vancouver. Their goal was to bring back to life, in robotic form, the Titanoboa ceruginoensis, a real snake that lived about 60 million years ago and is considered the largest snake ever discovered. But this project isn't just about engineering. The team also wanted to spark conversations about evolution, extinction, and our relationship with the environment. What makes Titanoboa especially remarkable is how naturally it moves. The team designed it to glide across surfaces using a side-to-side wave motion, much like real snakes. It can also inch forward by anchoring parts of its body while shifting others. A more advanced form of movement, sidewinding, used by some desert snakes, is still being developed. Next robot is a 1-meter-long vehicle that moves using two soft, undulating fins. Instead of traditional propellers, it relies on a unique wave-like motion, inspired by marine creatures like rays and squids. These hyper-flexible fins let it swim, crawl, jet, and even hop across different surfaces. Built for versatility, the Sea Ray can transition smoothly between water, land, snow, ice, and sand, all in one continuous mission. It's quiet, energy efficient, and able to operate with minimal disruption, making it a good fit for sensitive environments or stealth-focused tasks. Packed with sensors and smart systems, it includes GPS for when it surfaces, an inertial measurement unit, depth sensors, Wi-Fi, and GSM connectivity. It navigates using the Hydroman system and runs autonomy software through Moose IVP. It can quickly reverse, pivot in tight spaces, and handle complex terrain like coral reefs or cluttered underwater structures with ease. Autonomous operation is a major focus, and future versions are expected to work in coordinated groups, communicating with each other in real time. Funding has come from major US agencies. The Office of Naval Research backed it with $4.4 million in 2021, and followed up with another contract worth up to $8 million in 2024. Support also comes from the Department of Energy, the National Science Foundation, and research teams like MIT's Marine Autonomy Lab. The Sea Ray has been field tested for military missions like beach reconnaissance, mine detection, and special operations, including trials at Camp Pendleton. It's also built for environmental work, conducting coral reef surveys, tracking invasive species, and helping restore seagrass beds. In deep sea settings, swarms of sea rays could collect valuable minerals from the ocean floor without disturbing the ecosystem. It's even proven it can handle icy polar terrain, making it a flexible tool for missions just about anywhere. Here, we have a 4-legged robot designed to move and behave much like a real rat. It measures about 37.5 centimeters long from head to tail, stands 8.2 centimeters tall, and is 9.5 centimeters wide, weighing between 225 and 400 grams. With 13 points of movement across its spine, limbs, head, and tail, it can twist, bend, and walk with surprising agility. The robot uses a tendon-driven system where motors and pulleys mimic the function of muscles and joints to create smooth, natural motion. At its core is a central frame that holds everything together: legs, head, tail, battery, a Raspberry Pi for processing, and a custom spine control board. Its spine includes 8 flexible joints that let it curve and arch, while the tail has 21 segments that can swing from side to side. Each leg uses a simplified mechanical design that avoids traditional knee and ankle joints, instead relying on flexible materials to keep movement fluid. The Raspberry Pi acts as the robot's brain, managing tasks and communicating over Wi-Fi. 2 HD cameras are placed in the head for vision, while touch sensors on the head and nose give it basic tactile awareness. An onboard motion sensor helps it understand how it's moving in space, and the motors report back real-time data about their position and effort. Parts are made using 3D printed nylon, offering a good mix of strength and flexibility. The robot is easy to assemble, with plug-in wires and minimal soldering needed. NeRmo can walk, turn, and adjust its posture. It has been trained in simulation, using reinforcement learning to handle different terrains. Tests show its flexible spine helps it walk faster, turn more sharply, and stay balanced. Dolphin Spirit, also known as DEL, is a lifelike robotic dolphin that looks and moves almost exactly like a young bottlenose dolphin. It's about 8.5 feet long, weighs around 550 pounds, and has a soft silicone skin over a detailed internal frame that mirrors real muscle and bone. In the water, it swims, dives, turns, and even lifts its blowhole as if to breathe, creating a strikingly realistic experience. DEL is powered by a smart control system. Most of the time, it swims on its own using AI. But during live sessions, skilled operators can take control and guide its movements to interact with people, responding to gestures, nodding, and creating moments that feel genuinely alive. On a single charge, it runs for about 10 hours and is designed to last around a decade. This project comes from Edge Innovations, a team with deep roots in Hollywood animatronics and theme park technology. Led by Walt Conti, known for work on Free Willy, and Roger Holzberg, a former Disney Imagineer, the team has spent years bringing lifelike creatures to screens and exhibitions. DEL was created to address a serious issue: the ethical concerns surrounding captive marine mammals. Instead of keeping real dolphins in tanks, this robotic version offers the same sense of wonder and connection, without the harm. It's already earned praise from animal welfare groups and is just the beginning. Edge plans to introduce more realistic sea creatures, including sharks and whales, to bring powerful learning and entertainment experiences to aquariums, resorts, and museums. So far, the response has been overwhelmingly positive. Scientists, educators, and marine experts see it as a turning point, a new way to connect with ocean life without causing it any harm. The Great Elephant of Les Machines de l'Île à Nantes, France, is a towering, unforgettable machine. It stands 12 meters tall, stretches 21 meters long, and spans 8 meters wide. Weighing in at 48 tons, it's made of a steel frame, curved panels of tulip wood, leather, and an intricate network of hydraulics. It moves slowly, between 1 and 3 kilometers per hour, driven by hydraulic and electric motors, plus compressed air. Up to 50 people can ride inside at a time. With 62 moving joints, its legs, trunk, ears, tail, and even eyes come to life in a way that closely mirrors a real elephant's movements. A crew of operators steers and manages the whole system in real time using pedals, joysticks, and switches. This mechanical creature was imagined by François de la Rosière and Pierre Orefice and became the heart of Les Machines de l'Île when the project opened in 2007. Set on the old shipyards of Nantes, the site pays tribute to the city's industrial past while pulling inspiration from Jules Verne's wild stories and Leonardo da Vinci's mechanical sketches. Riders climb a staircase along the elephant side to enter. Inside, it feels a bit like being inside a wooden ship. There's a walkway up top for open-air views of the city, and along the way, displays explain how the machine works. The journey lasts about 30 minutes, during which the elephant walks its route through the area, trunk swaying, head turning toward bystanders. Every so often, it sprays water from its trunk, just for fun. Welcome to Shanghai Haichang Ocean Park. This is the home of the world's first robotic whale shark. Developed by Shenyang Aerospace Xinguang Group, is an artificial replica designed to closely imitate a real whale shark in both appearance and movement. It's about 4.7 to 5 meters long, weighs around 350 kilograms, and moves with the help of 7 motorized joints that control its tail, fins, and mouth. Each joint operates independently, equipped with its own sensors, processors, and communication tools. Instead of using propellers, it swims using flexible fins, allowing it to move more like a real animal and avoid disturbing marine life. It travels at speeds up to 0.7 meters per second and typically operates at depths of about 20 meters. It can be controlled remotely or set to swim on its own, following pre-programmed routes. On board, it carries cameras, sonar, a Beidou satellite positioning system, and sensors that measure water conditions. All this information is fed into a central system that helps the robot understand and react to its surroundings, adjusting course, avoiding obstacles, and mapping the area as it goes. The robot is being used in several ways. In marine science, it offers a way to explore underwater environments without harming them. It's also been introduced in aquariums to represent whale sharks without keeping the real ones, which are hard to care for and protected by conservation laws. There's also quiet talk of it being used in more secretive missions, such as surveillance, though those details haven't been made public. What do you get when you cross a pigeon with a drone? PigeonBot is a robotic bird with wings made from real pigeon feathers, 20 primaries and 20 secondary, attached using elastic bands that act like natural ligaments. Each wing is moved by 2 servo motors, giving it 42 degrees of freedom to adjust the feathers in flight. Its body is cut from foam board and supported by 3 D-printed parts, weighing about 255 grams. A front-facing electric propeller provides thrust, while a traditional tail with elevator and rudder handles pitch and yaw. The robot navigates using a PixRacer flight controller running ArduPilot, with data from a GPS, barometer, pitot tube, magnetometer, and a 50 Hz inertial measurement unit. What makes PigeonBot unusual is how it mimics the way birds fly. Instead of using separate motors for each feather, it relies on just a few joint movements in the wings to naturally align all 40 feathers. High-speed video of real pigeon wings showed that simple wrist and finger motions were enough to do the job. The feathers even connect using tiny hooks, similar to Velcro, that hold them together when extended and release when the wing folds. During test flights, PigeonBot showed it could turn sharply and stay stable, even in rough air. It handled wing adjustments mid-flight, sometimes flying with the rudder locked while steering only through wing shape. These trials showed that just changing the angle of the wings could guide the robot smoothly through the air. Researchers found that they didn't need complicated controls to fly with feathers, just a smart setup using the natural mechanics of bird wings. This opens up new possibilities for making flying robots that are more adaptable and responsive. The team is already working on the next version, with a flexible tail, more wing control, and eventually, fully autonomous flight and even flapping wings. MorpHex is a robot that moves in 2 very different ways. It can crawl like an insect on 6 legs or curl into a ball and roll. It runs on about 25 servo motors. Each leg bends and pivots with 4 degrees of freedom, and a single motor controls a central iris mechanism that reshapes the body through a set of Delrin gears. The shell comes from a 28 centimeters plastic globe, sliced into 12 curved panels. Its frame is reinforced with 2 mm aluminum plates for added strength, and all 32 servo channels are managed by a basic micro ARC32 microcontroller. Power comes from a 7.4 volt 5000 mAh battery. While control is handled wirelessly using an XB module and a remote like those used for RC cars or helicopters. MorpHex changes shape with 6 radial iris mechanisms. In walking mode, its legs fan out, and it crawls sideways using crab-like movements. When it shifts to rolling mode, the legs tuck in and the body panels close to form a sphere, allowing it to roll on smooth ground or downhill. There's also an in-between mode where it partially folds up to move with a tighter, more controlled gait and can pivot more easily. The first version of MorpHex started with a toy globe, which was stripped down and modified. Over time, it went through several updates. More servos were added, control software was adjusted, and mechanical parts were reinforced after some early failures. The newer version runs smoother, with stronger internal parts and better coordination between motion systems. Mondo Spider is a rideable walking machine with 8 legs that move using a system inspired by the natural rhythm of walking. Weighing around 1,600 pounds and measuring about 8 feet in every direction, it carries one person in a central seat and moves at a slow but steady pace, about 1.5 kilometers per hour. The legs all move in sync, driven by a central crankshaft. At first, it ran on a noisy 500cc gasoline engine, but in 2010, the team swapped it for a quieter, cleaner 2-kilowatt electric motor, powered by a 48-volt lithium-ion battery. It runs for roughly 2 to 3 hours on a full charge, which takes about 5 hours. Steering is limited and controlled by adjusting the leg cycles through a joystick or lever. The dashboard keeps things simple, showing speed, motor activity, and battery life. It was created in 2006 by a group of artists, mechanics, and engineers from Vancouver. They came together under the name Mondo Spider to build something different for Burning Man, a festival known for bold ideas and wild inventions. They weren't trying to build the fastest machine or the most practical one. They wanted to question why wheels dominate transportation and what it might look like to move through the world in a completely different way. Inspired by the leg designs of kinetic artist Theo Jansen, they came up with a walking pattern that looks oddly lifelike, even though all 8 legs move in lockstep. It's not robotic or responsive, it's mechanical and raw, with a rhythm that's more about presence than performance. Bee-Eater Technology designed a drone that flies like a red-crowned crane. Its wingspan is about 2.4 meters, right in line with the real birds. Instead of relying solely on motors, it uses a mix of flapping and gliding, so it doesn't burn through energy too quickly. If the motors stop working, it can still stay in the air by gliding. Inside the wings are electric motors, sensors, and tiny actuators that help it flap, steer, and adjust its pitch mid-flight. It can respond to wind conditions and battery levels on the fly, switching between different flight modes as needed. It's designed to cover about 150 meters at a time, but gliding stretches that range even further. The frame combines carbon fiber bones, flexible feather-like surfaces, and composite arms to keep it moving smoothly. This drone doesn't just fly like a crane, it looks and moves like one too. That makes it ideal for jobs where blending into the environment matters, like wildlife monitoring or nature filming. It can land gently, respond to different types of ground, and avoid standing out in natural settings. The drone made its first public appearance in 2019 at the World Robot Conference in Beijing, under the name Wind Rider. CEO Kai Yu said he looked to birds like the frigate, known for their incredibly long flights, for inspiration. The idea was to create something that could stay in the air for a long time while using minimal energy. But this project isn't just about engineering. The red-crowned crane holds deep cultural meaning in East Asia, symbolizing elegance and longevity. By drawing from nature and tradition, Bee-Eater has created something that doesn't just fly well, it flies with purpose. At less than 15 kilograms, the drone is close in size and movement to the real bird it's based on, and it's already being explored for use in film, research, and surveillance. NASA's Exobiology Extant Life Surveyor is a robotic system developed by the Jet Propulsion Laboratory to explore places no rover has gone before. It's about 4 meters long and made up of 10 identical segments that move like a snake, with each joint able to twist and turn in 3 directions. Weighing around 100 to 120 kilograms depending on its setup, it moves using a screw drive system that grips loose ground and also works in slushy or watery environments. Its front end is equipped with scientific instruments designed to collect and study samples right where it finds them. EELS don't rely on constant instructions from Earth. Instead, it uses onboard AI to make decisions as it goes, guided by sensors like LiDAR, stereo cameras, and internal navigation systems. Its computer systems constantly process feedback and adjust movements in real time. Since deep space missions come with long communication delays, EELS is designed to think for itself when needed. The robot is meant for terrain that other machines can't reach, like vertical shafts in ice, dusty slopes, underwater pockets, or underground tunnels. It can shift between climbing down, crawling across, or swimming through different environments. Even if one part fails, the rest can keep the mission moving. Its main goal is to search for signs of life, not just fossils from the past, but life that might be active today. A likely target is Enceladus, one of Saturn's moons, where jets of water shoot from the surface, hinting at a hidden ocean below. EELS could drop into one of those icy cracks and investigate the ocean directly. Since 2019, it's been tested in glaciers, ice caves, and terrain simulators. While not yet assigned to a specific mission, it's steadily moving toward readiness for future exploration, on distant moons, other planets, or even extreme locations here on Earth. Centauro robot is designed to step into places too dangerous for people, like disaster zones, collapsed buildings, or areas exposed to radiation. It moves on 4 legs, each with joints that let it walk, roll, or do a mix of both, depending on the terrain. With 20 degrees of freedom just in its base, it's highly adaptable and keeps itself balanced even on rough ground. On top, it has a human-shaped torso and 2 arms that can move in almost any direction. Each arm has 7 joints and ends in hands made to grip, turn, or lift real-world tools, just like a person would. These arms can be controlled remotely or work partly on their own, depending on the task. To understand its surroundings, Centauro uses a full set of sensors: 3D LiDAR to map depth area, stereo cameras to capture depth and detail, and motion sensors to track how it's moving. Sensors in its arms give feedback so it can interact with objects safely and precisely. All of this comes together in a system that lets it either follow human guidance in real time or carry out parts of a job on its own. The robot is controlled through a virtual reality setup. Operators wear a headset and use motion-tracked controls to guide Centauro as if they were inside its body. It can be fully driven by a person or run partly on its own, using software that plans paths, avoids obstacles, and recognizes objects. It even learns from its environment to get better over time. Centauro runs on battery power for up to 3 hours. It weighs about 93 kilograms and can lift up to 10 kilograms with each arm. It's already been tested in emergency scenarios, proving it can take on critical tasks where people can't safely go. This giant robot looks like something out of a sci-fi movie, but it's very real. It stretches 11 meters long, stands 3.6 meters tall, and weighs around 17 tons. It moves on 6 mechanical legs, but the actual weight is handled by hidden wheels underneath. 2 diesel engines power it, letting it move at a slow but steady pace of about 4 kilometers per hour. It can carry a driver plus up to 6 passengers inside its steel body. The cockpit is filled with control panels, and the whole machine can also be run by remote. Over 30 parts move as it walks: legs, joints, even the horn, which blows out smoke for dramatic effect. This isn't a team project or a company product. It's the work of one man, Hitoshi Takahashi. He started working on it in 1997 and kept going for 11 years until he finally rolled it out in 2008. The design was inspired by the Japanese rhinoceros beetle, or kabuto, and it shows in the long legs and massive horn. But unlike giant robot statues that just stand still, the RX-03 actually moves and gives people a ride. That sets it apart in a big way. Since its debut on Japanese television, it's made appearances at events all over the country. Watching it in motion is something else. The clanking legs, diesel engine noise, and bursts of steam make it feel alive. Riding inside feels more like controlling a machine than just sitting in a vehicle. This robot was developed by Tumsuk to inspect sewer pipes more safely and efficiently. It measures just 21 by 25 by 25 centimeters, or 28 centimeters tall with its camera, and weighs about 3.5 kilograms. Designed to move through pipes between 200 and 300 millimeters in diameter, it walks on 8 flexible legs that help it navigate bumps and debris where wheeled machines often get stuck. It comes with 2 camera choices: a basic Raspberry Pi camera with a wide-angle view, and a more advanced camera that captures everything around it in full 360 degrees, so it doesn't need to turn to look around. Bright LED lights at the front help it see clearly underground. The robot is powered through a wired tether using DC 12.5 volts and doesn't rely on batteries. Operators control it using a gamepad, similar to a video game controller, while watching a live video feed on screen. This setup makes it easy to use and allows real-time steering and viewing with no special training. SPD-1 can also work as part of a team. One unit might go ahead to scout the area, another can record detailed footage, and a third could eventually be fitted with tools to carry out repairs. This teamwork helps speed up inspections and covers more ground without needing to send people into risky spaces. The robot was developed in response to serious problems with Japan's aging sewer system. Out of roughly 490,000 kilometers of pipelines, 5% are already over 50 years old, and that number could jump to nearly 40% within the next 20 years. At the same time, fewer workers are available for sewer maintenance. SPD-1 is still being tested in real-world environments, but future versions may include features like wireless control, waterproofing, and use beyond sewers, such as in tunnels, factories, or disaster zones. Staying with our Japanese theme, let's now explore a robotic pet designed for emotional support. Moflin is a small, soft robot about the size of a kitten, 130 by 90 by 180 millimeters, and weighing just under 260 grams. It's covered in plush fur, available in gray or brown, and moves gently by tilting its head and squirming its body. Instead of legs or wheels, it relies on subtle gestures to react to the world around it. It comes equipped with 5 touch sensors, a microphone, and sensors for light, movement, and temperature. It squeaks and murmurs in response to interaction, adding to the feeling that it's alive in its own way. The battery lasts around 5 hours and charges in about 3.5 hours while it rests in its cradle, the Moflin house. Through Bluetooth, it connects to an app called MorpHex, which shows its emotional state, tracks how it's been feeling, and allows for basic adjustments like volume and updates. Moflin was created to offer emotional support in a simple, comforting way, especially for adults who may not want the responsibility of a real pet. From day one, it begins to learn. It remembers voices, recognizes how it's touched, and gradually reacts with more emotional depth. By about 25 days in, it starts showing more expressive reactions. By day 50, It forms a personality that feels distinct and familiar. The more it's handled and spoken to, the more it seems to form a bond, adjusting its behavior based on how it's treated. Its built-in emotional model helps it shift between moods like joy or unease, depending on daily interactions. This robot stands at 56.2 by 33.9 by 48.01 centimeter and weighs about 8.9 kilograms, roughly 40% less than the model before it. Under the surface, it runs on 12 high-torque cybergear servos across 4 legs, giving it impressive movement. It doesn't just walk or trot. It can jump, spin, and pull off backflips, even mimic dance moves and gestures. It moves at speeds up to 160 centimeters per second and can carry objects up to 1 kilogram. It's also smart enough to get back up on its own if it falls, thanks to training based on tens of thousands of dog movement simulations. The robot sees and senses the world through 19 different sensors. That includes a 13-megapixel AI camera, 2 wide-angle fisheye lenses, stereo infrared vision, 4 time-of-flight modules, and a LiDAR scanner. On top of that, it has touch-sensitive surfaces, ultrasonic sensing, UWB positioning, an inertial unit, and a 4-microphone setup. These give it the ability to recognize faces and gestures, detect obstacles, map its surroundings in real time, and navigate with pinpoint accuracy. At the heart of it is the NVIDIA Jetson Xavier NX module, with a 6-core CPU and a 384-core GPU powered by 48 tensor cores, together delivering up to 21 trillion operations per second. It's backed by 8 GB of RAM and 48 GB of total storage. The robot responds to voice through Xiao AI and can be controlled via gestures, Bluetooth 5.0, Wi-Fi, or UWB. It runs for about 90 minutes on a 4,500 mAh battery and recharges over USB-C. It's inspired by the shape and posture of a Doberman, and it moves with a similar mix of alertness and energy. This droid is 35 centimeters long and 63 centimeters wide, weighing just under a kilogram. Its body is made from a flat, rigid PVC-based material, while its fins, modeled after young manta rays, are crafted from flexible PVC sheets chosen after 2 years of testing 40 different designs. Instead of relying on traditional propellers, it swims using 2 motors, one for each fin, which set the fins into motion from a single point. As the fins move, their natural flexibility interacts with the water to create a smooth, flowing motion. It travels at about 0.7 meters per second, roughly twice its body length, and can keep going for up to 10 hours on a single charge. Inside, it carries batteries, control electronics, and space for sensors like cameras, sonar, and water quality monitors. Its quiet, fluid movement makes it a strong candidate for underwater research and observation, especially in areas where minimizing disruption is important. Tests in controlled environments have shown that it handles direction changes and navigation reliably. The idea came from a research team at the National University of Singapore, led by Associate Professors Chu Chi Meng and Yeo Kun Seng. Inspired by how manta rays move through water with steady, powerful flaps of their fins, the team set out to build a machine that could do the same. The hope was to reduce reliance on noisy, complex propulsion systems and find a simpler, quieter alternative. Developing MantaDroid took 2 years of fine-tuning how water moves around its body and how to best convert motor power into fin motion. Next steps include testing it in open water, building a larger version to carry more equipment, and experimenting with smarter control systems that help it respond more like real marine animals. Researchers at Tokyo Institute of Technology have created a half-scale robotic giraffe neck that closely mimics how a real giraffe moves. It's made from a series of 3D printed parts shaped like vertebrae, connected by flexible joints that act like ligaments. These joints give the neck a balance of strength and movement. Instead of motors, it uses pneumatic muscles, thin tubes that contract with air pressure, working like tendons. These muscles allow the neck to bend and twist in multiple directions. A stretchy band, similar to a giraffe's nuchal ligament, helps hold up the neck, taking some of the load off the muscles. For now, the system is supported on a fixed rig and doesn't stand on its own. Its movements are controlled by air valves, and while the exact method isn't fully detailed, it likely uses sensors to adjust pressure and positioning. The result is a neck that moves fluidly and naturally. It can handle contact and pressure without damage, similar to how real animals absorb impact without injury. This makes it a big departure from most robots that rely on stiff joints and motors, which often struggle to handle force or adjust to unexpected changes in their environment. This project builds on earlier work like the Kojiro humanoid robot, which simulates human muscle movement, and robots with leg systems powered by artificial muscles that can jump and react quickly. The robotic giraffe neck adds to this growing effort to create machines that move more like living beings. The team is now looking at how to manage the complex air systems that power the muscles and how to scale the design for larger, mobile robots. Their goal is to develop machines that can interact safely with people and handle challenging, unpredictable environments. Next robot is made up of 10 motorized segments that move from side to side, mimicking the way lampreys swim. Along each segment are pressure-sensitive sensors that detect how water pushes against the body. These sensors act like the skin receptors in real lampreys and send information to a simulated nervous system. That system has two parts working together: a central network that produces rhythmic muscle signals, similar to how a spinal cord works, and a peripheral layer that adjusts movement based on what the sensors feel. Both systems can be switched on or off, which lets researchers test how each contributes to swimming. AgnathaX was created to study how movement can be controlled by either internal signals, outside feedback, or both. Instead of using live animals, the team used this robotic model to control and observe every part of the process. When both systems were active, central and peripheral, the robot swam with the most stability, even when parts of the system were deliberately turned off. This suggests that, like real animals, it can adapt when something goes wrong. Even more surprising, when only the sensors were active and the central control was turned off, the robot could still coordinate its movement just through how the water moved across its body. It didn't need a central command, it figured things out through feedback alone. This helps explain how some animals keep moving after injuries to their nervous systems. MetaPanda weighs just 1.7 kilograms, but feels surprisingly alive thanks to 6 degrees of movement in its head and limbs. It runs for up to 12 hours on a full charge and powers up overnight via USB-C. Its fur is soft, hypoallergenic polyester, gentle on the skin, and the parts meant for touch are made from food-grade silicone. Measuring 57.5 by 39 by 19 centimeters, it's big enough to hug and small enough to carry. Inside, 8 sensors respond to touch on the head, back, cheeks, and limbs. Its eyes, two 1.89-inch LCD screens, show a range of changing expressions. A small speaker inside adds sounds that match its movements, from soft reactions to playful responses. The design is modeled after a 5-month-old panda, and the way it moves, snuggling, stretching, cuddling, comes from over 200 hours of real animal observation. Touch its head and it might nuzzle. Pat its back and it could give a little wiggle. Talk to it using one of 30 preset voice commands, or add your own wake word for a personal touch. When it's fed the included bamboo toy, it makes chewing sounds and lifts its head or limbs like it's really eating. Hug it close, and you'll feel a heartbeat, a gentle, rhythmic pulse that makes it feel warm and real. A built-in AI system reads every sound and touch, and then responds in ways that feel natural and emotionally aware. Every rover ever sent to Mars has had one thing in common: wheels. But are they truly essential? Let's hear what the developers of SpaceBok have to say. It is a four-legged robot designed to move in places where gravity is much lower than on Earth, like the Moon, Mars, or even asteroids. It weighs about 9.5 kilograms and stands roughly 0.4 meters tall. With a body length of 0.05 meters, each leg has 3 joints, similar to a hip and knee, which gives it a total of 12 points of movement. Its frame combines aluminum and carbon fiber, keeping it compact and easy to test in different research setups, including simulations of reduced gravity. The robot moves using brushless motors connected to precise gear systems that keep joint motion accurate and controlled. Sensors in the joints track position and force. While it's usually powered through a cable in the lab, it can run on batteries when needed. What sets SpaceBok apart is how it moves. It's not limited to slow, cautious steps. It can walk, trot, bound, or leap into the air. On Earth, it can jump over a meter high, and even higher when gravity isn't holding it down as much. Behind these movements are complex algorithms that help the robot plan its steps, stay balanced, and adjust its posture on the fly. Researchers have tested SpaceBok in a wide range of settings, on tilted surfaces, rocky test beds, and even during parabolic flights that simulate weightlessness. These trials help show how it could handle real off-world terrain. Though the first versions focus mostly on getting the movement right, SpaceBok also includes systems for sensing its surroundings. It has motion sensors, encoders in its joints, and force detectors.